All right, so this is the multiple choice grades. It's decent. The free response, I've asked the graders to have those completed by not this Thursday, by next Thursday. I would rather, so I usually 2 weeks is what I give them. I would rather them spend a bit more time and grade them well than to try to get them graded really quickly and for them not to be an accurate representation of the school. So that's generally my rules I give for free response. 2 weeks. That means that hopefully I should be able to put the free response grades in next Friday. And once I do so, I'll let you all know and all that jazz. From what I've seen, so again, I'm not going to talk too much about the tests and the makeups. Remember that, so I'm just going to talk about the rubric. Remember that if you choose the right equation, if you draw the picture, if you identify what you're solving for, if you identify the right equation, you're getting 50% of the points just from doing that on the free response. If not, then that's when it's not going to go well. Anywho, so those will get done when they get done. Again, this is decent. There was only 2 questions. So the reason there was a curve is there was 2 questions that only 35% of people got right. And so that's how I determined the curve, is that there's questions that a vast majority of people are missing. That means that I have not prepared you well in that area. No matter what I may think, the data shows that I haven't prepared you well for those questions. I will point out what those questions are on Thursday. And then I can almost guarantee variations of those questions will show up on the final. That's kind of how I manage that. If I didn't prepare you well, great. I'm going to point out what they are. We'll talk about them. And then on the final, they'll show up again. That's the idea. So, I keep lowering this because it sounds really loud. Okay, so great, there's that. Otherwise, yeah, I think that's basically it that I can talk about now. This week, my office hours are just makeups because I have to have people make up exams, and that's when I can slot them in. Next week, so this Thursday, I will post the exam with all the answers on it. So this Thursday, I'll post the exam with all the answers, including the free response. If you want to come see your test, your multiple choice, you can come to my office hours next week. I'll show you a Scantron. It'll be great. And you can kind of work through that then. And you can do that at any point. At any point in the rest of the semester after this week, at any point in the semester, you can come by and see your test. Do note, I obviously don't have the free responses done, so I won't be able to show you the free response until next week. Because it's the grades. So just keep that in mind. It's just the multiple choice I have. Alright. Cool. So, I'll chat more about the test on Thursday when I can. Yeah, the next exam is 4 weeks from this Thursday. So it should be in the syllabus. I believe it is November 6th. No, that doesn't sound right. 1 week, 2 week, 3 week, 4 week. Is it October 30th is our exam? All right, simple syllabus says, I don't have these memorized. If we go over to the simple syllabus, at the end of the simple, this is worth pointing out. It should be 4 weeks from this Thursday. We have 4 weeks worth of content, and then we have the exam is how I've planned it, so hopefully that should line up here. Yeah, there'll be a review that week. So 2049. Yeah, so if y'all go to the simple syllabus and you go to the very bottom. Oh, I get 5 weeks in there. How exciting. All right, November 6th. I thought I only had 4 weeks. I had 5 weeks. How good. All right, so there you go. November 6th is our next exam. 5 weeks of content, test 1, 5 weeks of content, test 2, and then, 1 or 2 weeks left over to cover what we can. Cool. All right. So, Another thing to note, this last week's quiz on resistors and current, I had forgotten to update the questions on it, so it actually had the content from this one. So if you took it and you're like, man, RC circuits, we haven't learned that, and power, we haven't learned that. I went ahead and just gave everyone the 5, I mean, everyone pretty much got the 5 points on it. That's obviously it's good to go. But I gave you the 5 points on it. I did update it to the correct questions. And what I'm going to do with that quiz is so you all get all the points no matter what. So there's no penalty to this. But if you do want this extra practice for like the final, what I'll do is I'll make last week's quiz, the one on current resistance, I'll make that one open till the end of the semester and give you all unlimited attempts on it, just for extra practice and stuff like that, because I made that mistake. This week's quiz is good to go. That'll open this week. So, what will be on this week's quiz? DC circuits. So we're going to finish up circuits this week. We actually don't have too much more to cover on it. We're going to talk about power. That's the last thing we need to get to in the PowerPoint slides. We're going to talk about the junction rule. We're going to talk about how voltage changes in a circuit. So there's 2 rules, junction rule and the loop rule. Together they make something called Kirchhoff's laws. Kirchhoff's laws are something that electrical engineers really need to know. Everyone else, but that's going to be a common narrative in this class. It's not. Oh, yeah. No, okay, so I'll point out one more thing. I just remembered something. Anyway, Kirchhoff's law, equations for adding series and series and parallel. We'll use Kirchhoff's laws. We'll do RC circuit. Sounds like a lot, but it's not too bad. Let me open this up. I also have your all's test feedback, and don't worry, this isn't going to affect anything for anyone doing the makeups. So always interesting. So if you didn't know, there's a survey. You get 2% bonus points on your exam if you do the survey, regardless of what you put. And I just want to show you all the results of this survey so you can see how you felt compared to other people. I always think that's interesting. And this is mainly useful for me, but it's good for you to know as well. All right, so I made a mistake on the first question. I should have said, have you taken Physics 2 before? Hopefully, yes, everyone's taken Physics 1 before, so that was kind of a wash. The goal here was to see if you'd taken like Physics 2 in high school or whatever. Whatever, it's fine. All right, how would you rate the difficulty of the multiple choice? It was actually higher than I expected. How would you rate the difficulty of the free response? Surprisingly, it wasn't that, there wasn't much room, I guess, above that. But they weren't actually super different. They're off by 1. Maybe everyone just thought everything was difficult. These questions I'm not super worried about as far as my teaching is concerned. As weird as that sounds. I'm okay with giving you all difficult things. There's 2 questions in here I'm really worried about. Not like the actual responses, but these are the ones I really look at. How would you rate the time given to complete it? So this was actually quite interesting. I expected people to, usually you almost always get like, not enough time, not enough time, not enough time. This is kind of interesting that it's not even like a normal distribution. It's a really weird, I don't even know what to call it, a plateau, I guess. I will say I am taking this into consideration, and I do think I'd like to give a little bit more time. So probably what I'm going to do on the next test is instead of so there's a free response, 3 free responses for 2 parts. Probably what I'm going to do on the next test is just have 4 free responses. You're like, that's 4. 4 free responses with 1 part each. 1 part each, and you'll pick 3 out of those. It's slightly less. Instead of having 4 questions you're answering, it's 3 on the free response. I might do that. Anyway, how much of problem sets did you go through? This is kind of interesting. You have people that did, and people I may who knows? Here's what they say. Varied. So, how prepared did you feel? Most people felt pretty prepared. That's pretty normal. That's good. This is the other question I really care about. There's 2 questions I care about when it comes to designing these tests. It's the time, and did I give you the right resources to prepare for it? Because those are the 2 variables ultimately that I can kind of do a better job at. I can either try to design the test to be more reasonable time-wise, or I can give you better resources. So I was really glad to see that people at least feel the resources I'm giving you are useful. Now, the last one, the survey, when I perused through it, and I always see this, is the most common request. So a lot of people said things are good. That's nice. I appreciate that. A lot of the things I saw, the most common request was more worked out solutions. That was the most common request. Now, What I'm going to tell you, and this is going to sound mean, I'm not going to end up providing more worked out solutions. But let me explain why I don't give you all a bunch of worked out solutions. There's a reason for this. So I do work out some in class. I think it is useful to see the process. The reason I don't provide worked out solutions to all the exams, the biggest reason is the most important thing you're going to learn in college is how to learn. So that sounds a little silly. How to learn. What do you do when you don't know how to solve a problem? Where do you go? Because in your job in the future, there might not be a worked out solution to the thing you're working on. There's not going to be a manual to go to. And so a lot of colleges, how do you find this stuff? How do you find the information you need when you don't know what to do? It sounds stupid, it maybe sounds like a cop-out, but trust me, it is one of the most important things. Do you know how to find what you don't have? Sounds stupid, trust me, it's incredibly important. Anyone who's in a programming class, it used to be one of the most important things that you're good at looking at stack exchange. Anyone who's a comp sci major has hopefully learned that every programmer out there, how do they learn how to program? You Google stuff when you don't know how to do it. The same is true of every one of your disciplines. Engineering, physics. Nowadays, it's instead of Googling, you want to chat. ChatGPT is a bit more efficient in those kind of things. ChatGPT, in my opinion, is kind of like a new Google. All the information is out there. All ChatGPT does is synthesize it for you. Does it mean it's correct? No, it still can make mistakes. Just like if you find a Google page, they can have the wrong answer too. That's still a thing.
I might be imagining things. Did you say there's going to be some like ChatGPT?
Yeah, there is AI. That's a great question. There is some AI assignments, and I'm meeting with someone to develop those, and I'll have those out for goals in the next couple of weeks. Because there is skills I think you want to work on. How do you take these problems? You can just take these problems and stick them in ChatGPT. And I do this to check my work actually on some of these. I will solve it out. But like anything, it's good to have someone double check it. ChatGPT is like someone else who can double check things. And it generates worked out solutions. Now, if it looks different than what you expect, you can just say, hey, what if I solved it this way? Would that work? You can ask follow-up questions. That is a skill that is new to ChatGPT. Googling stuff, you Google it, you see what you have. ChatGPT, ask follow-ups. Why did you do this? How do you do this? Could I do it this way instead? Why doesn't this work? Questions like that are the ways that you all need to learn and utilize this. Doesn't mean it's going to give you the right answers, no, but it doesn't. It's like 95% good, which honestly is going to be as good as like most people you go to. And another skill that you can use ChatGPT for is, hey, here's a problem. It shows you how to do it. Make different versions of this. Make variations of this problem, and then you do those without its help. Anyway, these are the kind of things. So this is why I don't provide them. It might sound like a cop-out. The other reason is people do get in the bad habit of watching someone do something and then saying that makes sense and never doing it for themselves. But that's a lesser reason. The bigger reason is I do want you all, I do work out some in class, but the reason I don't work out all of them is I want you to learn the skills of finding that information because it's far more important than the content I'm teaching you. How to learn is far more important. Your college degree shows that you know how to think, and when you're stuck, you know how to move forward. That's what engineers got to do. You're solving problems that people haven't solved before. Hopefully. If you're solving problems people have already solved before, you're not getting paid as much. So anyway, that's my little tidbit there. That I have reasons, and that's why. But you can always come to me, come to tutoring, like any of the SARC help room people. They can also help you with those worked out things.
So is the current problem set like up to date? The problem set 2?
The problem set 2 is updating for this week's content. Yeah, so it's kind of on a rolling basis where the questions are all. You have problem set 2 and you're like, why is it updating? Remember, I'm updating it to bring it to the level I wanted it to be at. So currently the questions there, I generally keep like half of them, but I like add some, remove some. Constantly updating. So this week for DC circuits is updated. Yep. All right, so, okay, let's get into stuff. So today my goal is to get through these first 3 bullet points. Technically this one as well, utilizing the junctions. And then next week we'll do the series in parallel in the RC circuits, and those will be pretty straightforward. There's no integrals in this. Yay? Yeah. In fact, this whole section, we're not actually going to have as many integrals because there is going to be integrals, but you'll see what I mean. There might be one or two cases where we can use them, but for the most part, there won't be a bunch for test 2. All right, so energy, power, energy, power. These are hopefully words you've heard before. You should have heard of physics 1. Power, this is just a reminder. Power is the energy converted per second. So power is something you should have learned about in physics 1, and you very likely saw it different than the form I wrote it here. You very likely saw power as work over time. That might have been how you saw it in physics 1. This is the same thing. Remember, work and the change in potential energy, those are the same, like a second bit negative sign, but we're not going to worry about that too much. How much, and it's not how much energy am I creating. It's not how much energy am I destroying. You can't create or destroy energy. So I'm not creating or destroying, I'm converting it from one form to another. So power, energy conversion. And it's this derivative because this could be you only turn it into this form W over T when W is a constant, when your work is constant. What if it varies over time? Which it might. Okay, but we're going to use this to derive the expression. So power equals d u dt, so derivative. What is power in terms of current and voltage? Hence, you need, you know what, I'll even give this to you. You need two relationships, and I'm going to give you one of them. Energy is Q times V, and we can use like little q if we want, but pretend like it's big Q. It doesn't really matter. This is one of the things I mentioned to you all, so that's the equation. Try that. See if y'all can derive this. So, when you plug this in and you do the derivative, notice that none of these have a Q in it because you also need to know the relationship between Q and I. What is current defined as? So I'll give you all a minute on this. P equals V divided by I, P equals IV squared, P equals IV, P equals V squared over I. There's one more equation you will need. Yeah, I'm going to give you all 20 seconds to think of it, and then I'll tell you what that equation is. The relationship between current... No, I'm not giving you the answer. I'm going to give you just the next step. What's the relationship between charge and current? You're going to need that as well. I'll give you that information in about 20 seconds after you thought of it. So. All right, so something from the last PowerPoints. What is current? It's how much charge per second flows through a wire. dQ dt. How much charge for how much time flows through a wire? It's rate of flow. All right, give you all 20 more seconds. All right, we'll close this out in 5, 4, 3, 2, 1. All right, so we're just going to plug the things in. This is how all derivations are done. You take a bunch of equations and you plug them in to each other. So great, there's my power equation. And then I'm going to put where U is. I'm going to put what U is. It's Q times V. I even tell you in this problem, V is a constant. If V is a constant, you can pull it out. So you have V times dQ dt. What is dQ dt? Oh, that's current. Look, you all just derived the power equation. PIV. P equals IV. That's the derivation for it. Now, something I want to point out, because I did see this in the feedback as well. So, reminder to you all, before the test, I sent out a PowerPoint slide with all the clicker questions in it. And I sent 2 versions. I posted in the Files tab. Someone mentioned that, it's helpful to not have all the answers there. Reminder to you all, if you have PowerPoint, if you download the PowerPoint and you go to the Review tab, there's a button here that you can hit called Hide Ink. And all the answers are gone. If you click it again, they reappear. So just to make sure everyone's aware that that exists. And you can do this for any PowerPoint at any time. That's why I upload both versions. So, great. Cool, PIV. There you go, power. It's the amount of energy. And I say lost or gained. It's probably better to say changed to another form. The unit is watts. I can almost guarantee you've seen the word watts before. If you've ever bought a light bulb, every single light bulb is some watts. 10 watts, 20 watts, 100 watts. They used to all be 100 watts. The LED ones nowadays are like 14 watts or so. 14 or 20 watts, depending. The variable is P for power. That's nice. P equals IV, and by using V equals IR, you can get 3 different versions of it. You just swap it in there, and you get P equals IV, P equals I squared R, P equals V squared over R, just by using that equation and swapping in the 2. If you're like, what is he talking about? So if you just take this if you take V equals IR, and you just put it where the V is, you get P equals I squared R. Try it for yourself. On the formula sheet, I only give you P equals IV, and I give you V equals IR. It's up to you to assemble the different types if you want them. All right, so to this end, just to make sure we understand what power is, so for example, when you all buy, let's say, a 14-watt LED light bulb, it's a pretty standard wattage. What that means is every second, it's taking 14 joules of electrical energy and converting it to something else. Actually, a whole bunch of things. Mostly it's getting converted to light, but some of it does get converted to heat. Potentially some other things. That's basically 99.9% what it converts it to. Every electrical appliance in your house is a wattage. If you all buy a generator tells you the output wattage, and it's got 2 different ones. It's got like a max one, and then it's got like a sustained one. When appliances turn on, they require, so when your fridge turns on, it requires a bunch of wattage at first, and then it stabilizes. There's reasons for this. So a generator can do that super amount for a little bit, and then it decreases. All this to say, this is something super useful. I had to go through this exercise when I was last year when there was a hurricane. I decided to buy a generator. I didn't want my freezer and all that stuff for everything to go bad. If it was power for a day or 2. What did I need to figure out? I needed to figure out the power of my refrigerator. But in fact, it doesn't tell you. What it does tell you in your refrigerator door is it tells you the current. It tells you the voltage. Just multiply them together and you have the wattage that your refrigerator uses. And by doing that, I was able to determine my refrigerator, I was able to determine my freezer, I was able to determine a window AC unit and make sure that the wattage of those combined did not exceed that of the generator. Practical use cases. But at the end of the day, something I also want to point out with this that you don't need to know, but it's important or it's interesting. This gets to the heart of why electricity is useful. Something you probably you're like, of course electricity is useful, but why is electricity useful? Electricity lets us take energy from one location to another and then convert it to something we actually want. None of you are using electricity in its quote-unquote raw form. None of you are making little lightning bolts of electricity. What are you using electricity for? To change it to a useful type of energy. Heating, cooling, which is kind of the opposite. Moving things, mechanical motion. All electricity is just basically liquid energy. It's energy you can transport and then change to something that you want it to be really easily. That's why electricity is such a big deal. That's why it's so useful. And you can then, do almost anything with it nowadays. Light, heat, motion, like that gets you through most things. So, just an interesting thing that most people don't think about. They're like, great, electricity, it's useful for me. But this is why. It's easy to convert from one type to the other. And we've already learned heat is really simple. Just run it through a resistor. Boom, you made heat. Like that's a really easy way to make heat. How do you make motion? We're going to learn that in about 3 weeks' time. How do you take electricity and convert it to motion? 3 weeks' time, we're going to learn how. So, for the sake of, okay, I'll work through this one quickly. It's not bad. A heater is being designed that uses a coil of nichrome wire. There's its resistivity to generate 300 watts with a voltage of 110 volts. The wire is 14 gauge, which is an awful unit. That's the US way of measuring diameter. It's awful. Fun fact, the smaller the gauge, the thicker the wire. Stupid. In Europe and stuff like that, they just tell you the millimeters. Wouldn't that be nicer? You could actually get a caliper and measure any of them. I have a bias towards this. Great, it's got a diameter of 1.627 millimeters, so we can actually do something with this. How long should the engineer make the wire? This is a very practical application. You want to make a space heater? You want to generate a certain amount of heat energy per second? This is what you're going to do. Like, this is very functional. All that to say, something I really want to point out, this was a problem on the test, specifically for response. What am I solving for? You should write the letter for what you're solving for before you start the problem. Why? That immediately tells you what equations are going to be relevant. If you know what letter you're solving for, you're going to choose the right equation. If you don't know what letter you're solving for, good luck. First step, know what your target is. What am I solving for? Length. What is the variable for length? L. You both need to know what you're solving for, and you need to know the letter that represents it. If you are missing either of those, it's going to go south. So I need length. We then go to our formula sheet, and there is only a single formula with an L in it. That's probably the one we're going to use. So if you go to the formula sheet, we scroll on down. No, it's not in this folder. Formula sheet. If you know what variable you're solving for, okay, so there is some extra ones with L, but that we haven't learned about those yet, so it's probably not going to be that. Look, there it is. It's the only equation with an L in it. Probably going to need it. R equals rho L over A. Resistance equals rho L over A. We then look at this equation and we say, let's rearrange it. We know we want L, so let's just rearrange it now. Why not? So we have R times A over rho, just algebra. Resistance. Well, I don't know resistance, so probably going to have to find that. Area. I have the diameter of the wire. I can find the area. Resistivity. That's also given in the problem. So I have this. In fact, I'll write this R times pi R squared. Every single wire. No one's giving you square wires. Wires are always circles because it's easier to make them that way. We have R. It's just half of this. Diameter divided by 2. Boom, that'll be my radius. We have resistivity. It's right up here. We don't have R. How do we find R? We look at our formula sheet and we say, what equations have R in them? That's going to be my options. We have V equals IR. And there is technically, let's just look at this one for now. V equals IR. All right, we got V. That's good. I want R. Oh, I don't have I. How can I find I? Let's find another equation with an I. This is like even if you don't know anything about what you're doing, this process, I don't understand even if you don't understand what these equations are doing, this process still works. That's the power of equations and understanding the variables. Rearrange this. R equals V. Now, ideally, you understand what these equations represent and all that. That helps out a lot. But anywho, so great. V over I. And it's like, great, I don't know I. How can I find I? There's another equation with an I in it. P equals IV. I have P in my problem. I have the power. It's 300 watts. I have the voltage. It's 110. I can find I. With I can find R. With R, I can find the rest of it. So this process I just went through, I didn't explain I didn't have to understand a single one of these equations. What I did have to know is I had to understand the units and what variables they correspond to. This will get you through a lot of equations in your future, a lot of your classes in your future, even if you don't understand what you're doing. If you can at least understand the equations, what equations exist, and what variables you have, that can get you pretty darn far.
Is that rho or p rho?
Yeah, that's a good question. So whenever I do a P, I'll try to make the P, it's capital P. Rho is it doesn't have the little, yeah. So a P is this, and then a rho is like a lowercase tilted. Yeah.
This question, we want to convert the diagram.
100% we need to convert, yeah. So this is also something that showed up a bunch in the test. You got to convert your units. You all are going to be working. Look, no one's measuring the distance to their house in millimeters or centimeters or meters. No one says how far away is my house. And if we're in like imperial units, no one says is this many feet. It's how many miles. But every equation is calibrated for base units. There's a reason we use these unit conversions. No one can understand how far if I told you something is 7,320 feet away, you're going to have no idea how far away that is if you think of it in feet. If you convert it to 1.5 miles in your head, you can then get a sense of it. Your brain can't do big numbers. Sorry, it's just not built to do it. Your brain can't do big numbers. Your brain, fun exercise for you to figure out how big of a number your brain can imagine, it's just a fun mental exercise, is imagine a crowd of people and imagine how big can you make that crowd such that you can recognize everyone in that crowd. It's a kind of a weird exercise, but it gives you a sense of how good of a number your brain can imagine. I can imagine a crowd of 100 people in my head. I can get a rough sense of how big that is. I can maybe get a sense of about 1,000. Maybe. I'm starting to stretch it there. Once I get above 1,000, if I try to imagine a crowd of 1,000 people in my head, it's going to look... I'm not going to have a good estimate of that. Your brain can't do big numbers. Why? It's psychology. I don't know why. Just can't. All right, but anywho, if we put all these pieces together, so something I did here is I kind of walked through this. It is useful to just identify. You can make this nice little list. Whenever you're doing a problem, it is useful to make a little list of what you have. So I didn't do this in this problem because I was just working purely in variables. But this is helpful, and I can take this and make it into radius by dividing it by 2. Great. And I have resistivity. So there you go. But anyway, there's all my units. But yeah, as far as down here, so I is going to equal P over V. I am then going to take this and I'm going to put it down here. So my R is going to equal V over P over V, which is going to equal V squared over P. P equals V squared over R, like it all works. Great, and then you're going to take this, and then you're going to put that where R is. And at that point, it's just plugging in numbers. So you're going to see me a lot working purely in variables. But plugging in the numbers is a useful exercise to do on the test. There was stuff where you had to plug in numbers. I often just don't do it in the class because it takes some time. And is it worth spending that time? With you all, I'm not too worried about it. I think you all can plug the numbers in on your own. If this is an algebra-based course, I would spend the time plugging in the numbers. But you all have hopefully plugged a lot of numbers into a lot of equations, so I trust you to do that. But be careful on these unit conversions. Super common mistake I see on things. Not the reason most people miss questions on the exam, though. So.
Yeah, that's interesting because the last slide it had V squared over R.
Yep, it's the same thing over here. If you rearrange this, P equals V squared over R. They're the same thing, just rearranged. We just derived it different way. Yeah. Yep. All right. Now, something to remind ourselves. So this is something we've already chatted about, but let's see if you remember. How does the flow of water through the top paddle compare to the flow of water through the second paddle? We've already answered this question. See if you remember the answer. Is the top one get more water, less water or the same amount of water flowing through it per second. Flow rate. Give you all 20 more seconds. All right, in 5, 4, 3, 2, 1. All right, so how does the flow compare? Let's see how we did. Oh, great job, great memory. It's the same. Great job, great job. This is one of those important rules. And what does this represent? What does this flow represent? The current. Current is the flow of charges, just like water is the current is the flow of water. We use the same word for both. Use that to help you understand it. All right. Now in this situation, and it's a little subtle here, so I made it clear, I made it explicit. How does the flow of water through the left wheel compare to the flow of water through the right wheel? Do note that this left wheel is thinner than the right wheel. I know that's maybe tricky to see in the picture, so that's what I'm telling you. This one is thin. This one is thicker. You can, if I zoom in, you can see that. So, how does the flow of water compare between these two? Is it faster flow in the left wheel? Is it faster flow in the right wheel, or the same flow? To clarify, the left wheel is the thin one, the right wheel is the thicker one. So how do those flow rates compare? And let me re-clarify the wording here. I'm going to, instead of saying the word faster, let me say more. Yeah, let me say more. I don't really care how fast the water is moving. I care about the amount of water going through it. The amount of water going through it. Is it more water through the first one, more water through the second, or same in both? Per second. All right, 20 more seconds. All right, in 5, 4, 3, 2, 1. Now, in the last problem, the flow was the same because they were in series, one after the other. You couldn't get to one without going through the other. You got one highway. You're stuck behind a semi, you're going to go the speed of that semi. In this one, we have two paths you can take. One that's narrow, one that's wide. 2-lane road versus a 1-lane road. Which one are you going to be able to get more cars on? The one that's bigger. There's more room, more water can fit through it. It is not held up behind the other wheel. This is the difference in parallel. The voltage is the same. The height difference is the same. Water will take the path of least resistance. So will current. Now, it happens when there's only one path, you don't get a choice. The path of least resistance is the only path available. In this one, I have a choice. And you can physically see here that like more water can fit through the wider one. So what does this get to the heart of? This gets to the heart that current can take different paths if available. And it will choose the path of least resistance.
Wait. But the light blue is at the water.
Yeah.
So the light blue is more of that.
It's just covered up a bit more. That's just orientation. You got a 2-lane road versus a 1-lane road. Which one can cars go faster on? Which one can more cars go through? Yep. All right. So current in a circuit. This kind of puts the ideas together. In a circuit, current is constant along a branch. What is a branch? It's a line of wire. It's a line of wire, and you have branches and you have junctions. This red line up here is one branch. Why? Because there's only one path along that. You know, like a tree. You got a branch. Junctions are when it splits. So each of these like lines that I'm coloring here are different branches. Different paths. When they intersect, when they come together, we call that a junction. Think of it like an intersection in a road. When you get to an intersection, you have a choice. You can go one way or the other. How many choices might you have? There's all different types of intersections. I can have 100 wires intersecting at a junction. There's no rule to how many wires can intersect. It's how many you can fit in there and what you want. So in this case, this is like a road that there's like you're going along, you can keep going straight, or you can make a right turn. But I could easily have more wires come in here and more options. There's no rules against that. What is important here is that the current will split. So if the current is flowing into here, let's just pretend like it is, and let's just pretend that it's flowing out and flowing out here. We're making things up. Whether or not that's correct, we'd have to actually do a bit more work to determine that. But the current going in will split between these two. How will it split? It depends upon what's going on in each branch. You can't just look at it and tell. Sometimes you can look at it and tell. Other times you got to do some math. It's not trivial. It's not a 50-50 split. It's going to take the path of least resistance. Which path is the path of least resistance? You might have to do some math to figure that out. That might not be a trivial answer. Sometimes it's obvious. One path is a big resistor, one path is a small resistor. That's pretty obvious. Other times it's not. So we're going to learn how to do it when it's complicated. We're learning the basic idea, and then we'll learn about what's complicated. But the important thing here is that it will split, and what goes in must come out. If I have 200 students enter this room, if my room is empty at the end, 200 students left. Now, which door do they leave from? I don't know. It doesn't really matter to me. But what comes in must go out. The same is true of current. If 10 cars go into an intersection, if 8 go one way, 2 are going to go the other way. What goes in must come out. Not a crazy idea. It's something you're familiar with. You just need to connect it to current. What goes in must come out. If you add up all the currents that go into a junction, it will equal all the currents that go out of a junction. Why? If I have 200 students go in a room, and my room is empty at the end, 200 students left my room. Otherwise, where do they go? Like, someone's hiding in my room or something. Like, no, that's... What goes in must come out. Otherwise, you're going to build up current in this junction, and that just doesn't make sense. Why would it stay there? There's no reason for it to. So what goes in must come out, and in this example here, notice we draw the direction of the current. You need to know what directions are in, you need to know what directions are out to make this judgment call. In this picture, I have I1 going in, I2 going in, I4 going in, I5 going in. How do we know they're going in? They're all pointed at the junction. Which ones are going out? I3 and I6. Why? They're pointed away from the junction. Again, nothing here should be like crazy. It's stuff that you have seen. So I'm just going to color code them here just so you can see that maybe a bit easier. Very simple rule based on your experience and reality. But it's a very important rule. This is the first, there's 2 Kirchhoff's laws. This is the first one. It's called the junction rule. You also might hear this Kirchhoff's law number 1. Same thing. Kirchhoff is the guy that came up with these. They're laws because, again, this is just how things work. What goes in must come out. Why? That's how the world works. Where did it go otherwise? Yeah. So, based on this image, what's the value of I4? See if you understand. In this picture, I have a junction in the middle. On the left, I got wire 2 with 2 amps pointed towards the junction. I have 5 amps pointed towards the junction, 7 amps pointed away from the junction. And then I'm asking for I4. What's the value of the current through that wire? Is it 3 amps, 6 amps, 4 amps, or 0 amps? What goes in must come out. All right, give you all 20 more seconds. I'm actually going to give you a problem about this. In fact, I'm going to take this one and pull it backwards. And we'll figure that out. What happens if they said, what if you guess wrong? Because these are all good guesses. I think the current two is this way. What if I'm wrong? What happens? We'll see. Yeah. All right, 5, 4, 3, 2, 1. All right, what goes in must go out. That's the rule. This is an equation on your formula sheet. So what's going in? My 2 and my 5. So 2 plus 5 equals what's going out? My 7 plus my I4. So we get 7 equals 7 plus I4. What does I4 equal? 0. This was on purpose. It is possible to have a wire with no current flowing through it. That's allowed. Just because there's a wire doesn't mean there's current flowing through it. I mean, you all know this. Pick up a piece of wire. If it's not plugged into something, there's no current flowing through it. Another case is maybe we have a capacitor that's fully charged and it's not letting any more current onto that capacitor. The current will stop flowing through that path. That is a reality. That's actually a very useful mechanism. We're going to learn about that at the end of this PowerPoint. That capacitors can be used as a timing circuit, where basically you charge this capacitor and it takes a certain amount of time to charge, and once it's charged, the current stops flowing. I have something that has a certain time period now. I can basically make the current flow for a certain amount of time and do stuff with that. Yeah?
How does it like, quote unquote, choose where to go?
Yeah, great question. How does it choose how to go? In this picture, there's not nearly enough information. And so something when you solve these problems, and actually we're going to see this in I'm going to make another version of this right now. When you're doing these pictures, either I will tell you the direction of current, or you won't even make a guess. And it's okay if you're wrong. So I'm going to show you what happens if we make a guess on current and it's wrong. And it will be perfectly fine. The math will fix it for us. So this is something important. When you're doing these circuit diagrams, you have to make a guess. You say, I think current's going this way. If you're wrong, it works out fine. It will correct itself when you do the math. So let's actually do that. Someone asked the question while we were doing this, and it's a great question. What if they were all pointed inwards? What if every current was pointed inwards? So let's do that. Let's do this exact same problem. I'm going to delete all the ink on it. And we're going to see what happens if we point them all inwards. So I'm going to take this arrow and I'm going to make it point the other way. I'm going to make this I4 and I'm going to make it point the other way. Unfortunately, I do need to make this multiple choice. But I'm going to let you all experience this for yourself. I will make some multiple choice answers for it. There we go. So say I gave you this picture. In the image below, what is the value of I4? So, I'm going to give you all some time to think about it before I put all the answers. So I'm going to leave this here. These are not the answers. I'm going to put the answers in a second. But before I put some answers, I want you to think about what the answer might be. So spend some time as if you're answering this question. I will send it to you to answer. But if I put the answers, it's going to give something away. Try it out. Do the same process you just did. So yeah, do the same exact process you just did. Build the equation. Sounds stupid, but the answer will reveal itself when you do. All right, so I put some answers up here. Is the current through I4 14 amps, 0 amps, negative 14 amps, or negative 7 amps? Yeah, we kind of do direction that's like negative, like we've seen before. I don't think it's kind of sort of that depends on how you do your definition. All right, I'm going to give you all 25 more seconds. In 5, 4, 3, 2, 1. All right, we're going to do the exact same process. Sum of current in equals sum of current out. What's going in? Everything. So we have I1 plus I2 plus I3 plus I4 equals what's going out? Nothing. 0. Plug in the numbers. 2 plus 5 plus 7 plus I4 equals 0. Do the math. What does I4 come out to? Negative 14. What does that mean? It means when we made our guess, it was wrong. It fixed itself. So this is what will happen if you do the math, which we're actually not going to do with these math. If you make your guess on the picture and it's the wrong way, that's fine. The math will spit out a negative. Once it spits out that negative, you're not going to update all your equations. You'll just plug that negative in, and it'll update them for you. When you plug in the negative, it'll automatically update it to be like, oh, it should have been on the other side. So, it's great. So when you're doing these problems, and if you have to draw current, pick a direction. I don't care. Just pick something, and it'll work out. So great. Negative 14. And that just means that the correct answer, the current's actually going to flow to the right. These Kirchhoff's laws are fundamentally used in any circuit, like anything online that determines how current flows through a circuit. This is a fundamental rule it's following. Now, on to the next rule. Voltage. We talked about current. What about voltage? What's happening with voltage? How can you change the voltage? There's 3 ways. Only 3 ways. A battery. Okay, sorry, there's more than 3 ways. There's only 3 ways we've covered so far. A battery, a resistor, and a capacitor. And then I'm going to put in all bold, in all caps, because, again, a junction does not change the voltage. A junction does not change the voltage. Just because the path splits doesn't mean that my height suddenly drops in one direction. So to give you all a sense, again, we got this nice picture, which I'm really pleased with. Look, here's a junction. Does my height change? No. Height is like voltage. When does it change? When it goes through this resistor. So, when we're going across a battery, a resistor, or a capacitor, my voltage will change. How much does it change? In the case of a battery, it's whatever the voltage of the battery is. In the case of a resistor, V equals IR. That's how much my voltage changes. The current times the resistance. In the case of a capacitor, C equals Q over V. Rearrange that for V equals Q over C. That's how much my voltage changes. Now, there is something I didn't mention here. Whether or not my voltage goes up or my voltage goes down depends on a few things. And it varies based on each of these. So we're going to practice that now. When does it go up? And this is how much it's going to change by. Am I increasing my voltage or decreasing my voltage? We're going to look at specific examples to understand that. All right. So do I want to do this one? Yeah, this is simple. I'm going to give you all 40 seconds. This is easy. I mean, like, that wasn't the reason for not doing this because it was difficult. But which way will current flow? I have a battery here. The positive side is the high voltage. The negative side is the low voltage. And then I have some resistors. Which way will current flow? Remember, current is defined as the direction positive charges, quote unquote, move. So which way will positive charges move? Will they go from high voltage to low voltage or low voltage to high voltage? All right, give y'all 20 more seconds. All right, in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right. Current is defined as the flow of positive charges. Positive charges are going to want to move away from high voltage and towards low voltage. That's just the rule. You can also think about it, which way are positive charges? They're going to get repelled by this positive, attracted to the negative. So, on the top part, current's going to flow to the right. On the right side, it's going to flow down. On the bottom, it's going to flow left. On this side, it's going to flow up. You put all that together and you get clockwise. Notice I couldn't just say current's going to flow to the right, current's going to flow to the left, because it has to go in this loop. Flow of water. You can't have current going to the right on the bottom and down on the right side. That makes no sense. So like if I drew this picture and I said current's going this way, this makes no sense. I have two currents flowing into each other. That just doesn't make sense. It's a one-way road, y'all. It's a one-way road. So, great. There's my current. It's important to realize this, though. In a problem, I might only tell you that current flows down through a certain resistor. You can figure out the direction it flows in every other resistor by just, it's going to go around the thing. Yeah. Yeah, that is a good question. So the question was, I thought only electrons move. You are correct. Electrons will move the other way. That's the reality of what's happening. But Benjamin Franklin defined it as positive charge flowing. So here we are. Yeah. It's not the reality, but it does the same job. All right. Current flows from high to low. Therefore, voltage drops when we go across a resistor and in the direction of current. Why? I start at 12 and I end at 0. For that to happen, each time I go through one of these resistors, it's going to drop until I get all the way down to 0. When you're going in the direction of current, you're going from high to low. When you're going in the direction of current across the resistor, where you start is the high end, where you end is the low end. Because that's why it's going through the resistor at all. Why is it going through the resistor? There's a height difference. It goes through that. It goes downhill. It's going downhill. So, great. That's how we determine the resistor. What about the battery? If I'm going through a battery, my voltage is going up. Why? If I go from the negative terminal to the positive terminal, I went from low to high. You can just kind of see that from the picture.
The resistors don't fully block the current.
Correct. The resistors never, no matter how big your resistance is, some small amount of current will flow through it, assuming it's a conductor. Yep. All right, so here's a nice picture of this. This is a picture showing the voltage as you go through this circuit. It's the exact same circuit. When you go through the battery, it goes from low to high. Why? Because the negative is low and the positive is high. It's a ski lift. Think of a battery like a ski lift. It lifts up that height difference. I hit one resistor, I drop by IR. I hit another resistor, I drop by IR. I hit another resistor, I drop by IR, because I'm moving in the direction of current. Current is flowing this way, so I'm going from high to low, high to low, high to low. And then in the case of this circuit, it loops back around and the cycle continues and yada, yada, yada. So we're kind of looking at like one electron's or one proton's journey. Whatever. There's a nice little visual of this height difference. Yeah. Yeah.
At what point do they die?
Yeah, at what point do they die? When the generator, why is the ski lift running? Someone's got to put fuel into it. When the fuel runs out, the ski lift stops operating. What's the fuel in this case? The chemicals inside the battery. When that chemical reaction, when those chemicals, you run out of your reactants, they've all turned to product, you're out of fuel. So in that ski lift analogy, think of the chemicals as like a gas that you're plugging in the generator to make that happen. Yep. In the case of rechargeable batteries, you're able to reverse that reaction. You're able to get that gas back. The analogy falls apart a little bit, but you're able to reverse the chemical reaction. Yep. All right. So, what is the change in voltage? If I start at some point, I loop around and I end where I started. So, pick any point on your circuit. I don't care where. Pick point A, pick point B, pick point D, pick point C. Start there. Get some voltage. Go back around. How is my voltage? How is that? What's the change in voltage from one point to itself? If you made a loop around, you ended back where you started. Is it 12, 6, 3, or 0? Just random spots on it. Yeah, they're just points. They don't mean anything. So yeah, pick any spot on the circuit, start there, make a loop, end back where you started. What's my change in potential? Change in potential, what's my potential difference? What's my electrical potential? What's my voltage difference? All right, 20 more seconds. Yeah, I really like this problem. All right, 5, 4, 3, 2, 1. All right, we're going to use the height analogy. Conveniently in this room, I can make a big old loop if I wanted to. It's going to take me too long, so I'm not going to do it. I start at this point. Pretend like I make a giant loop around this entire room, and then I end back where I started. What's my change in height? 0. What's my initial height? I don't know, pick a number, 5. I make a loop. What's my final height? 5. What's 5 minus 5? 0. If I pick a random spot over here, and I say I want to start on the stairs over here, and I make a giant loop, so let's say my height now is 7. I make a giant loop. My initial height 7. What's my final height? What's 7 minus 7? Voltage is like height. If you start and end at the same spot, how much did your height change? None. Why? At some points you went up, at some points you went down. When you come back to where you come back to, you got to be at the same height. Voltage is like height. If I ask you how much my height changes and I'm at the same exact spot, if you close your eyes, you wouldn't even know I moved. So let's look at this picture and maybe understand that. If I pick this spot, let's say that this voltage, let's say the high point is 12, the low point is 0. It's a 12-volt battery. So if this is 12, this is 0, great. I start at 12. I make a big old loop and I end back where I started. 12 minus 12 is 0. It sounds like once you know it, it's hopefully you're like, oh, duh. Hopefully. If not, think about it more. This is not asking I'm not counting my steps. So if we use the height analogy, I'm not counting the absolute value of how much I went up and down. I'm not counting my change in altitude. Like when you run, you sometimes do that. You like measure your, not just how far you traveled, but you also measure like your height differential, but absolute value. No. This is just, if I start and end at the same spot, I haven't moved. I haven't gone up or down. There's zero change. I don't care where you pick on this circuit. I don't care where I started in this room. If I start and stop at the same point, what's my change in height? Zero. I went up, I went down, it all cancels out. Same thing, if we look at this picture. If I started up here at the high point and I make a big old loop, oh look, I ended back where I started. Pick any spot and that follows. So, this is a law. This is the second law. It's called the loop rule. The loop rule says, and again, don't worry, if you missed this, you're not alone. That's why I really like this question. The loop rule says, if I make a loop and I end where I start, I don't care what you make that loop, as long as it doesn't cross itself or do something weird, actually it didn't have to cross itself. Make a loop, make a circle, end where you start, your change in voltage is zero. All the ups and all the downs will cancel out because you got to end where you started. So, there you go. Very important law. I know it's you're like, oh wait, I moved up and I moved down. But it all cancels out. So this is the second rule. And with these two rules, these form Kirchhoff's laws, and these two laws let you basically understand the flow of current in any circuit. These two laws alone are pretty good for almost any circuit. Now, you do have to learn what resistors, capacitors, and eventually inductors are. There's a lot of circuit elements. But any software that's determining how current flows through a circuit, they're using these two laws. They're the fundamentals. And we're going to practice them, and we're going to build these equations. I will spare you from solving the equations, because they end up being a system of equations. We'll get 3 equations with 3 unknowns, which just takes an unnecessary amount of time to solve. But I will ask you to build the equations. Just like the integrals.
It's not that hard. It's not that easy.
It's in my opinion, it takes a while. These systems of equations take a while. They're just if any of you are in statics right now, you're having a great time with systems of equations. It just takes a while, and I don't want to waste the time on that. Anyway, all right. This is a nice little summary of what we've been saying. When does voltage go up? When does voltage go down? We need to know this. And we're going to build the sum of voltages. If you're going in the direction of current across the resistor, voltage goes down. If you're going opposite the direction of current, voltage is going to go up. And you might not be able to see these arrows. Unfortunately, the contrast isn't too good on here, so I'm just going to outline them for you all. On my computer, they look way nicer. That's the direction of travel. That's the direction of travel. You can't really see them super well in here, but just trust me.
That's not the current, right?
No, their current is labeled below that. The current in this one is going to the right in both cases. In the bottom, I'm going to outline those arrows for you. On my computer, the contrast is nice. It's just not nice on the projectors. Something you don't realize until you're teaching it. If you're going from negative to positive on a battery, voltage goes up. If you're going from positive to negative, voltage goes down. Are you going up the ski lift or down the ski lift? All right, so let's apply this to this problem. This is actually, we got close enough to where I wanted to, so we're going to do this one, talk about the answer. If I go clockwise in the following circuit, what is the equation for the total voltage drop? Assume a current I in the circuit, and look, I even told you which way I is. It's the direction we picked before. It's shown down here. That's the direction of current. Notice I only drew it on one part of the circuit. You're going to need to find it in every spot. Build this equation. The sum of voltages equals 0. Notice all these equal 0. Go through your loop. So what you're going to be doing, pick a spot to start. Then you're going to start going through your loop. As I go through the battery, should my voltage go up or down if I'm going in this clockwise direction? It tells you which way to go. So as I'm going through this, when I go through the battery, does it go up or down? When I go through the resistor, does it go up or down, and how much? When I go through this resistor, does it go up or down, and by how much? When I go through this resistor, does it go up or down, and by how much? And then we end at the beginning, and our sums equal 0. Try it. Build it. Add up the voltages, and I will, look, okay, and these answers, if you want, it really doesn't matter where you start, but in this case, the way I built these, I guess you could say I start here. Addition is, it doesn't order the order. Pick any spot, but we'll just say start there. Try it out. I'm going to give you all a whole 2 minutes for this. Loop your way around. Am I going up or down by how much? This is a very easy free response on a test to give. Or sorry, multiple choice. This is too easy for free response. Yeah, this is pretty easy. I like it. You know what you're doing? Notice they all get the same I. They're in series. A couple things over here if you're looking for stuff.
I just Apple Pencil.
I haven't seen one.
That's fine.
Yeah. I mean, feel free to keep looking through that.
Oh, it's fine. If it's not there, I'm not here today.
Yeah, sorry. Hopefully
We're good.
there's the math office on the second floor. Sometimes things are lost and found.
All right. Appreciate it. Thank you.
All right, you got like 30 more seconds. Go through your loop, and it's how much am I going up or down, and by how much? That's all we're doing. All right, maybe just 5 more. We're stalling on. I think people are going to answer it. So 5, 4, 3, 2, 1. All right, so we're going to build this equation. What's very helpful is, one, you draw the loop. We call this the loop rule. You should draw the direction you're traveling. And it's also helpful to draw the directions of current through every resistor. So great, we do that. So we hit this first resistor. I'm going in the direction of current. Current flows from high to low. So I'm going to go down. How much am I going to go down? I times R. This first one's R1. We'll get to R2. So right now we're at this guy. Next, we're going to hit the next one. It's a sum. Oh, you're right. Oh, that's sad. Pretend like this was R2 and R3. I have no idea. Oh, why did they do this? All right. Hopefully you realize that these are 1, 2, 3. It doesn't, whatever. The next one. All right, so sure, we'll call this one 2. The next one we're going to hit. And we're going to hit the next one. It's going to go down as well. Why? It's in the direction we're traveling. So that's a minus sign. Next, we're going to hit the battery. Am I going to go up or down? Up. Next, I'm going to hit the resistor. And I'm going to go down. And boom, that's my answer. A bunch of negatives in front of the resistors. You have to build this. There's no it's always negatives for IR. It won't be. We'll see some examples where it's not next time. We'll practice this a couple times more. Have a good one, y'all.